Thank you so much for the introduction. I'll be discussing some joint work that I've done with Sylvie Cortiel and Olia Mandelstam, and separately with my student Donghyun Kim. And by the way, I probably won't be very good about monitoring the chat, so a moderator is welcome to do that for me, or people can just unmute themselves and ask questions. So let me start by giving an overview of the talk. I'll be talking about several different characters, as it were. The first one is a model from probability and statistical mechanics called the multi-species asymmetric simple exclusion process. The second character is combinatorial polynomials, and I'll talk quite a bit about a family of polynomials called Macdonald polynomials. And then the third character in the talk is combinatorics, and in this talk that will be some objects called multiline queues and also tableau. And so the first sort of half of my talk, I'll be discussing these three objects and their relation to each other. And then I will whoops, sorry, wrong direction. And then I will switch to a slightly different version of this model. I'll be talking about the inhomogeneous multi-species ASEP, which is also a model of particles hopping. And then I will discuss some different combinatorial polynomials called Schubert polynomials and the combinatorics that is related to both of these things. Okay, so let me start by defining the asymmetric simple exclusion process, or ASEP. This is a model that was actually introduced by biologists in 1968 and independently by a mathematician, Spitzer, in 1970. And in this model, you have particles hopping on a one-dimensional lattice. There's at most one particle per site. That's the word exclusion in the title. And particles can have different weights, which affect their hopping rates. So in this model, there's different choices for our lattice. The lattice could be a line with open boundaries, or it could be a ring. And it's this latter example that I'll mostly be talking about. And the ASEP has been cited as a model for traffic flow, sort of one lane of traffic. It's also been cited as a model for translation in protein synthesis. And quite a lot of people have studied it. This is a very incomplete list of names of mathematicians and physicists who have studied the exclusion process. Okay, so now let me get a little closer to actually defining the ASEP on a ring. So we're going to choose a parameter t between 0 and 1. And then we're going to fix a lattice of n sites arranged into a ring, and we'll choose n particles, each of which has a weight, which is some non-negative integer. And given my n particles with their n weights, I will sort those weights in weakly decreasing order. And that gives me a partition, lambda, whose components are lambda 1 through lambda n. So as an example, if I'm talking about particles hopping on this circle, you can see here my particles have weights 1, 2, 2, 0, 0, 0, 3, and 2. If I sort these weights in weakly decreasing order, I get this partition lambda. And here n is 8. That's the number of positions on the circle. Okay, so in this model, we allow two adjacent particles to swap places at rate 1 or t, and the rate depends on whether the heavy particle is clockwise of the lighter one. So I've drawn t's and 1's here, and whether it's t or 1 depends on whether the heavier one is clockwise or counterclockwise of the lighter. Okay, and there's many questions you could ask. One of them is, what happens as time t goes to infinity? What are the steady state probabilities? Okay, so now let me actually define this even more carefully as a Markov chain. So states of lambda is going to be the set of all words, also called compositions, obtained from lambda by permuting the letters. So remember, lambda was my set of weights that I see in the lattice, sorted into weakly decreasing order, and now states of lambda is all permutations of those. So if lambda is this 3, 2, 2, 2, 1, 0, 0, 0, then my set of states gets identified with all of the words I can make using 1, 3, 3 2s, 1, 1, and 3 zeros. And when I think about states of this Markov chain as words, what I'm doing to go between the circle and a word is choosing some arbitrary but fixed place to cut my lattice, and then I just read the numbers clockwise. So each mu is a composition, it's in states of lambda, it's viewed on a circle, so it's sometimes helpful to be able to talk about mu sub n plus 1, which is the same as mu sub 1. And now the multi-species ASEP is the Markov chain on states of lambda with the following transition probabilities. So if mu is a particular state, so this is a word, and here capital A and capital B are shorter words and I and J are 2 letters in the middle. And if nu is the same word, except these particles of weights I and J have swapped places, and if I is bigger than J, then the probability of going from state mu to nu is T over N, and the probability of going from nu to mu is 1 over N. So this is how I'm defining my, my transitions in the Markov chain. And in any other situation, the probability of going between 2 distinct states is 0. And the probability of staying in the same place is what it needs to be, namely 1 minus the probability that we exit that state. Okay, so this is a little picture of the Markov chain when I have 3 states. So there's 3 sites on my lattice. So n is 3 and lambda is 2, 1, 0. So I have particles of weight 0, 1, and 2, and they can they can swap places. 2 adjacent particles on my circle can swap places. And so I have 3 factorial different states. And this is the state diagram that shows the different ways and probabilities of transitioning between 2 states. Okay, so if you solve for the steady state probabilities, so this is the distribution you get if you let time go to infinity, then you get the following probabilities. So the probability of 0, 1, 2 is the same as the cyclically shifted word 1, 2, 0, which is the same as the probability of the cyclically shifted word 2, 0, 1, and it's 1 plus 2t over 9 plus 9t, and the probability of the other 3 states is this 2 plus t over 9 plus 9t. Okay, so this is a very small example, which you can just solve using linear algebra. But even for much larger lambda, the probabilities continue to look nice, where by nice, I mean they look like polynomials with positive coefficients with not too many terms. And so if you're a combinatorialist and you see the stationary distribution and you see you can express it using nice looking polynomials with positive coefficients, it's natural to ask, is there a combinatorial formula for all of these steady state probabilities? Okay, so maybe I should pause and see if there's any questions about the definition of the model. Okay.
I have a question. Is there, as the lambda gets bigger, like here you had sort of 2 choices. How many choices are there in gen? You know, do things tend to be equal? Is it? I guess it's always up to symmetry. Is that right?
Yes, it's always up to symmetry. So because of the cyclic symmetry inherent in the model, you'll always, you'll
just
always
get orbits.
Yes.
Okay.
Yeah. So if all of my weights were n distinct numbers, then instead of having n factorial different probabilities, we should look for n minus 1 quantity factorial. Okay, so now let me shift gears a little bit and talk about Macdonald polynomials. So we say that a polynomial f in variables x1 through xn is symmetric if for any permutation pi in Sn, my polynomial f is the same as the polynomial I get if I permute its variables according to pi. So for example, x1 plus x2 plus dot 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 plus xn is symmetric, and so is this polynomial. So elementary symmetric polynomials are prototypical examples of symmetric polynomials. And the set of symmetric polynomials forms a ring, which has been well studied in combinatorics and representation theory. So this ring has several very nice bases. The monomial symmetric polynomials m lambda, which are obtained by taking a monomial x to the lambda and then adding all terms you need to add in order to make it symmetric. More importantly, the Schur polynomials s sub lambda. So the dimension, yeah. So okay. So the bases for this ring of symmetric polynomials are indexed by partitions lambda. Here, partition means weakly decreasing list of numbers. And the Schur polynomials, if you haven't seen them before, they arise as representations of the general, as characters of polynomial representations of the general linear group. And they also arise as cohomology classes of Schubert varieties in the Grassmannian. So the Schur polynomials are extremely important throughout mathematics. So symmetric polynomials and various bases of the ring of symmetric polynomials had been well studied. And then in 1988, Ian Macdonald introduced a new family of homogeneous symmetric polynomials called P sub lambda. And these are polynomials in the ring of symmetric polynomials adjoin Q and T, and they're indexed by partitions lambda. And these so-called Macdonald polynomials are uniquely determined by the following properties. So there's an inner product, the Macdonald inner product, that makes them orthogonal. And there's also a kind of a triangularity property where the Macdonald polynomial P sub lambda is the monomial symmetric polynomial plus monomial symmetric polynomials indexed by partitions mu, which are less than lambda in the dominance order on partitions. So, so this is how people generally define Macdonald polynomials. I realize if you haven't seen them before, this is not a way to get any intuition about Macdonald polynomials. But I'll show, I show here an example. The Macdonald polynomial P sub 210 is this monomial symmetric polynomial plus this rational function Q and T times this monomial symmetric polynomial. Yeah, and I guess the way to think about, if you're not familiar with Macdonald polynomials, just think about them as sort of QT generalizations of Schur polynomials. Okay, and in particular, when Q equals T equals 0, they specialize to Schur polynomials, and also if you just set Q equals T, they give back Schur polynomials. So let me just say a few facts about the Macdonald polynomials. I mentioned already that they generalize Schur polynomials, and they also generalize other well-known polynomials like Hall-Littlewood polynomials and Jack polynomials. Macdonald made a famous positivity conjecture for how they expand in the plethistic Schur basis, which was eventually proved by Mark Heyman by making a connection to the Hilbert scheme of endpoints in the plane. And even though they were introduced in 1988, there was no combinatorial formula for the Macdonald polynomials until 2005. And this was given by Haglund, Heyman, and Lohr. And there are also some non-symmetric versions of Macdonald polynomials denoted E sub mu. And for the purpose of this talk, really, the most important thing about Macdonald polynomials is that a certain specialization of the Macdonald polynomials is the partition function for the multi-species ASEP on a ring. So the thing that's most important to this talk is that they have a probabilistic interpretation, and that was realized by Cantini, De Geer, and Wheeler in 2015. So I'm using the terminology here, partition function for ASEP of lambda. So what I mean here is that if you look at the steady state probabilities for ASEP of lambda, so these probabilities are going to be rational functions. You can write them as ratios of polynomials in T. If you take these ratios of polynomials in T and you find a common denominator for all of your steady state probabilities, that common denominator is what we sometimes call the partition function, and that common denominator is the specialization of the Macdonald polynomial piece of lambda when all the xi's and q is equal to 1. Okay, so that's how these two things are connected. We have this Markov chain, and then we have the Macdonald polynomials, and this certain specialization of Macdonald polynomial, where you set almost everything to 1, gives back the partition function for this Markov chain. So when Cortiel and Mandelstam and I saw this, we decided we would try to use the combinatorics of multi-species ASEP to try to understand Macdonald polynomials better. So that was the impetus for our work. And so now I want to tell you about the combinatorics of the multi-species ASEP. Okay, so Ferrari and Martin, who are probabilists, had introduced these things called multiline Qs in order to study the ASEP. And so our goal was to take these combinatorial objects used to study ASEP to try to understand Macdonald polynomials better.
May I ask you a question?
Yes.
Why would you think that you could detect things about Macdonald polynomials when, from these models, you specialized everything was equal to, all the variables were equal to 1 except for 1?
Right.
You must have had some other reason.
Not really. No, I mean, it's true. It feels like you're throwing away almost all information about the Macdonald polynomial since you're setting nearly all of its variables except for 1 equal to 1. So I don't know, maybe we were, maybe it was kind of a wild goose chase that we embarked on, but it worked. So yeah, I don't know. Yeah, I guess we wanted to understand what Cantini, De Geer, Wheeler had done, and we wanted to see if we could upgrade any of the combinatorics used for multi-species ASEP to understand Macdonald polynomials.
Thank you.
So yes, so I was starting to talk about multiline Qs, and so so I have to tell you about what's a ball system. So we're going to fix N and capital L positive numbers. So a ball system B is an L by N array of positions which are either empty or filled with balls. So it's very simple. I have my columns labeled from 1 to 8, and I have my rows labeled from 1 to 3, and some spots are empty, and in some places I have balls. And okay, there is some kind of condition where I want lower balls in lower rows to be more, I want to have more balls in lower rows than in higher rows. Okay, so we're going to view this thing on a cylinder. So our rows are going to wrap around. And now if I have a ball system, a multiline Q for this ball system is going to be a kind of a matching of balls from row R to row R minus 1. So I'll just show an example. Oh, and right. And so how should you think about these things? So the way Ferrari and Martin think about them is that our balls are like customers and services. And when you match balls to other balls in the row below, the higher ball is like a customer who's looking for a service, and they are going to choose some service in a lower row. And then, yeah. Okay, so a multi-line queue is constructed via the following rules. So every ball B gets matched to any ball B prime in the row below. And when I connect them, I will use the shortest strand that travels either straight down or from the left to the right. And I allow wrapping around. So here I have a ball, which is going to look at the available services at the row below. It's going to choose this ball, and then I connect them with this shortest strand that's moving from left to right. And since my initial ball starts in row 3, I'm going to label both of these balls by 3. Okay, so I match all my balls in row L to some partners in row L-1, and then I match these partners to new partners in row L-2, and so on. And all of those balls I label by the same number, namely the label of the topmost row. Okay, so in the first step, I matched these 2 balls, and in the next step, I matched this ball to this ball down there. Okay, and then you sort of recursively do this, continue this process. You take your unmatched balls in row L-1 and you repeat the process. I will read my unmatched balls in row L-1 from right to left. And if at any point there's a free unmatched ball B prime directly under ball B that we're matching, I have to pair them. That's called a trivial pairing. And maybe one way to think about it is that if you are so think about this ball right here. When this ball is trying to choose a service, since there's a service sort of literally parked right in front of him, it's too rude to sort of bypass that service. And so out of courtesy, he will accept the service. Okay. Okay, so this was this kind of trivial pairing, and now I'm going to proceed from right to left. This ball here is going to look at all of the unmatched balls below, and it decides to skip over these 2 services, wrap around, and then accept this service down there. And then I continue. The last unmatched ball in row 2 is this one, and it's going to choose this ball down here. And finally, the only unmatched ball is this one, and that's going to not match to anyone because there's no one in the row below. There's no row below, and it just gets a 1. Okay, so this is a multi-line queue. The type of the multi-line queue is the word at the very bottom. So in this example, if you read the labels from left to right, you see 2, 2, nothing. So that's a 0, 0, 0, 3, 2, 1. Okay, and now there's going to be a weight of every multi-line queue. That's a function of qt and the xi's. And so the way I associate a qt weight to each multi-line queue is I look at every non-trivial pairing. And okay, it's not too important to digest this definition. I'll say briefly what it is, but it doesn't matter that much that you really memorize this definition. I'll maybe just explain it in this example here. So let's look at this red pairing. So I'm matching this ball 3 to the partner down here. And so my weight function is telling me I'm going to have a factor of 1 minus t, that's this one. And then t to the number of skipped balls. Well, when I matched my 2 balls labeled 3, I skipped over this ball here, so that's 1 skipped ball. And then I divide by this ratio, so 1 minus q to the I minus r plus 1. I is the number of the ball, and r is the row where it started. And then t to the number of free. So number of free balls means how many choices I had when I chose that pairing. there were 4 choices when I chose this pairing. So that's a 4. And then this factor over here, if the pairing wraps around the circle, I'm going to pick up a factor of q, and otherwise nothing. Okay, so anyway, so the details are not too important, but there's a simple QT weight associated to every pairing. Okay, I could go through all those examples, but maybe I won't bother unless somebody really wants. Okay, so now the weight of a multiline Q is the product of the weights of all of its pairings times a monomial in x's that just keeps track of how many balls are in each column. So the x weight is very simple. So the QT weight here, it came from the QT weights associated to all my pairings. And then this x weight here is just telling me how many balls there are in each column. So for example, this is column 1, this is column 2, 3, 4, 5, 6, 7, 8. And so for example, if you look in column 6, I have 2 balls, and that's why I have an x6 squared here. Okay, all right. So the upshot is that we have some combinatorial objects called multiline Qs, and they each get associated to them a weight, which is a function of Qt and x. And now one can use this combinatorics to give formulas for Macdonald polynomials. Okay, so let's let lambda be a partition, and mu is any composition obtained by permuting the parts of lambda. So now this f sub mu is going to be the expression I get if I sum over all multiline Qs whose bottom row is mu, and I sum up the weights. Okay, so f mu is like the generating function for multiline Qs whose bottom row is mu. And so now I can state some results. So if we let lambda and mu be as above, then there's several things we can say. F sub lambda, so this generating function for multiline Qs, equals the non-symmetric Macdonald polynomial E lambda. F sub mu is something called a permuted basement Macdonald polynomial for arbitrary compositions mu. And if you want to understand the actual Macdonald polynomial P sub lambda, then what you do is you sum over all states of your Markov chain. So that's mu, compositions you can get by rearranging the parts of lambda, and you add up the contributions F sub mu. So yeah, so it's a new formula for Macdonald polynomials, and you get it by summing up weights of Macdonald polynomials whose bottom row is some permutation of lambda. Okay, so this here is just a review of my notation. So in addition to being able to understand Macdonald polynomials using this combinatorics, we also get a new proof of something that Martin had proved, which is a formula for all of our steady state probabilities in the multi-species ASEP. So remember, the multi-species ASEP didn't have these parameters x, i's, and q. It only had hopping rate t. So what you do to understand the steady state probabilities is you specialize all these variables, all the xi's and the q's to be 1, but you use these quantities f mu and z lambda. F mu is the generating function for multiline q's whose bottom row is mu, and z lambda is the sum of all of the f mu's, where mu varies over your states. And then your steady state probability of being in state mu of the ASEP is f mu over z lambda. So using these multi-species, using these multiline Qs, we can understand two things. One is the Macdonald polynomials, and one is the steady state probabilities. So here's a small example. The multiline Qs with bottom row 2, 2, 1, 1, 0, 0 are the following 7 objects, and I've put their weights underneath them. And so then by the theorem, the sum of the terms above equals the non-symmetric Macdonald polynomial. And I mentioned earlier that Hagelin, Heyman, and Luhr around the year 2005 had found the first combinatorial formulas for Macdonald polynomials in terms of some tableau. So one thing that's nice about our formula is that it seems, well, experimentally, it's shorter. It's shorter than their formula. It has fewer terms. So I don't have it on this slide, but if you use their formula to understand the corresponding Macdonald polynomial in this example, they have, I don't know, 9 terms instead of 7. So in general, our formulas are shorter and a little bit simpler than theirs. Okay. And in this,
sorry, Lauren, can you explain, is the corollary meant to be evident, or is it that?
No. No.
These MLQs are used to understand the I forget what they're called, the ASEPs.
Yes.
I see. So that's where you got the, okay. Thanks.
So, yes, so Martin had written a paper that inspired ours that used multi-line Qs to understand steady state probabilities. Yes, so we give so that's why I said it's a new proof of his result. He got to a very similar result using a different proof. Yeah, so the result we have is new for Macdonald and is a new proof of Martin's result on steady state probabilities. Okay, so in this same example, if you specialize the parameters xi and q to be 1, then you get the unnormalized steady state probabilities of being in state 221100. Okay, and then if we wanted, so that was for this non-symmetric Macdonald polynomial capital, which is called capital E. And if you want to understand the symmetric Macdonald polynomial, then you have to sum the weights of all multi-line Qs whose bottom row is some rearrangement of lambda. So to compute, for example, this Macdonald polynomial, you have to add up the weights of multi-line Qs whose bottom row is any permutation of 3, 2, 2, 2, 1, 0, 0, 0. Okay, so this is just one of the terms. By the way, if any of you are familiar with Schur polynomials, and especially the semi-standard tableau combinatorial formula for Schur polynomials, then it's a nice exercise to see how to give a new formula for Schur polynomials using our multi-line Q formula for Macdonald polynomials. So basically, you can take our multi-line Q formula, set Q equals T equals 0, and then it's a not too hard exercise to see that our formula is kind of bijectively corresponds to semi-standard tableau. Okay, so just as a little summary of what we've seen this model from probability and statistical mechanics, the multi-species ASEP. We've seen that it's connected to Macdonald polynomials, and we've seen that the combinatorics of multi-line Qs can be used to understand both of these things. And let me just make a remark that this ring where the particles are hopping looks like a type affine A Dynkin diagram, and also the usual Macdonald polynomials are associated to the type affine A Dynkin diagram as well. So that, of course, begs the question, what about other Dynkin diagrams? And more generally, what happens if we tweak our Markov chain? So we could change our lattice, or we could change the hopping rate. By the way, I don't know if the background noise is evident on my side. My 5-year-old is having a little violin lesson on Skype, so sorry if that's distracting. Okay, So anyway, so I raised the question, what happens if we tweak our Markov chain? And there's several ways we could tweak it, either by changing the lattice or by changing the hopping rate. So here's one thing we could do. We could change our lattice, and instead of having particles hop on a ring, we could have them hop on an open line, like a line with open boundaries where particles can enter and exit at both sides. And this is a model that we studied at length some years ago. And this model turns out to be connected also to some combinatorial polynomials, in this case, Askey-Wilson polynomials and Kornwinder polynomials. Kornwinder polynomials are actually Macdonald polynomials of type C, F and C. And there's also some very nice combinatorics that you can use to understand these things, and it's these staircase tableau. So anyway, I'm not going to talk about this story, but it's just to say that you do get something beautiful happening when you change the lattice in this way. And instead, I'll say a few words about a different parallel story, which is what comes about when we change our hopping rate. So let's keep our particles hopping on a ring, but now we're going to refine the hopping rate. So recall our particles have all different weights, and now I want my hopping rate to take into account the weights of the particles that are being interchanged. So you can see here that 1 and 4 are my weights of particles, and the rate at which they get interchanged will be x1 minus y4, where the x's and y's are some parameters. And when you look at this version of the ASEP, you also get some beautiful combinatorial polynomials, but this time they're Schubert polynomials, double Schubert polynomials, if you keep your y's. And multiline Q's also play a role here. Also the combinatorics of some permutations that we call evil-avoiding permutations. And so I'll say a little bit about this story, which is based on joint work with my student, Dong-Hyun Kim. Okay, so I just want to be really clear on how I'm changing the setup from what I talked about before. So remember, the multi-species ASEP on a ring was this setup where two particles swap places at rate t or 1, just based on who's heavier than who. And instead, in the homogeneous ASEP on a ring, our hopping rate depends exactly on the weights of the particles. And here, because I want to emphasize this connection with Schubert polynomials, I'm going to require that all the weights that appear are distinct numbers, because I want to identify my states with permutations. So here my state shown, if I cut my lattice right here, then I get the permutation 1, 4, 6, 2, 7, 8, 3, 5, and that's this. And I'm going to make one little restriction, which is that I only allow adjacent particles to swap places if the heavier one is clockwise of the lighter one. So I'm not going to allow this 5 and 1 to swap places. I will only allow particles to swap places when the heavier one is clockwise of the lighter. So this 4 is clockwise of 1, and here 6 is clockwise of 4. So I'm showing here all of the allowed swaps. Okay, and otherwise two adjacent particles cannot swap. Okay, so recall that in our previous setup, the multi-species ASEP had probabilities that were closely related to Macdonald polynomials, which are some QT generalizations of Schur polynomials. But what about probabilities for the inhomogeneous ASEP? So you can, again, work this out for small examples. And this is what you get when n is equal to 4. So let me explain what my notation here is. So this math frac S stands for the Schubert polynomial associated to a permutation W. And I'll define Schubert polynomial in a moment. So this is the case where n is 4. And so we have 4 factorial or 24 states, but because of the circular symmetry inherent in the model, I only need to write out the probabilities for the permutations which start at 1, right? Because the probability of the state, which is a cyclic shift of any of these, is going to be the same. Okay, so what we see here Oh yes, and let me also say, in this table, for simplicity, I've set my y parameters equal to 0. And I've also, sorry to give all these caveats, I've also renormalized the probabilities so that they appear as polynomials as opposed to ratios of polynomials. But I'm sort of putting everything over a common denominator and then clearing that denominator. Okay, now I think I've told you everything you need to know about this table. Okay, so what we see here is that our probabilities in this example look like monomials times Schubert polynomials. So Schubert polynomials are a different generalization of Schur polynomials, and they represent cohomology classes of Schubert varieties in the complete flat variety. So this is also a very interesting generalization of Schur polynomials. So let me now define them.
Lauren?
Yes?
Can you go back a minute, because I'm confused a little bit about this model. If we're in state 1, 3, 2, 4,
yes.
I'm just wondering, how do you get there, right? Because doesn't that mean that 1, 3 is bigger than 1, that's okay, but then 2 versus 3, right? I'd never be allowed to make that. I'd never be allowed to be moved into that. Right? I mean, I'm just.
So did you say 1, 3, 2, 4?
Yeah.
So you can always do a swap whenever your heavier one is clockwise of the writer. So here we can, so you're asking how would we get to 1, 3, 2, 4?
Right. Right. If you were right, I mean, if you were in some random initial state.
So 1, 2.
But I mean, so I'm just, yeah, I mean, I'm sorry, I just need to think it through or something.
Oh, right. Well, from a given state, you can always go somewhere. You can always go somewhere because there's always
there's always the 4 and the 1,
yes.
or whatever, right?
Yes.
And then
yes.
that's what makes there not be
a sink or something.
A sink, right? Okay,
yes.
got it. Okay,
yes.
All right. Thank you.
Thank you for asking.
Sorry for interrupting. Okay.
Oh, no. Thank you for asking. Okay, so what are these Schubert polynomials? So let me define what's called divided difference operator. So if we have a polynomial p in n variables, p of x1 through xn, then the divided difference operator del I is defined as follows. What you do is you take your original polynomial p, and then you multiply, sorry, you take the same polynomial, p, but you interchange xi and xi plus 1. So this difference of polynomials is going to be divisible by xi minus xi plus 1, so then you divide by that quantity. Okay, so that was the divided difference operator. And this divided difference operator you might associate to the simple reflection or simple transposition SI, which is the permutation swapping I and I plus 1. But now if SI1 through SIM is a reduced expression for a permutation in Sn, then one can check that the concatenation of divided difference operators, del I1 through del IM, depends only on W and not on the particular reduced expression that we chose. And so in effect, we can talk about the divided difference operator associated to a permutation W. Okay, so let's let bold X and bold Y be two sets of variables, and we'll let this delta of X comma Y be this product of Xi minus Yj's. And now to every permutation W, we can associate what's called a double Schubert polynomial, first defined by Lescaut and Schutz and Berger. And what you do to define your double Schubert polynomial, S sub W, is you start with this delta xy, and then you act by the divided difference operator del, which is associated to the permutation W inverse W naught, where W naught is the longest permutation. So W naught is the permutation that sends 1 to n 2 to n minus 1, and n to 1. Okay, so it's a very concrete definition of these double Schubert polynomials. And if I want to drop the word double, then I just set all my y's to be 0. Okay, so that's what I just said. Ordinary Schubert polynomials are just obtained by setting the y's to be 0. And when W in Sn is what's called a Grassmannian permutation, it has only one descent, then the corresponding Schubert polynomial is a Schur polynomial. So in particular, both Macdonald polynomials and Schubert polynomials generalize Schur polynomials. But now Schubert polynomials have a very nice geometric significance, which is that they represent cohomology classes of Schubert varieties in the cohomology ring of the complete flat variety. And there's also a geometric interpretation for the double Schubert polynomials, now in terms of equivariant cohomology. And there's been quite a lot of work on the combinatorics of Schubert polynomials, starting with work of Bailey, Jockish, and Stanley around 93. Okay, so now let me show the steady state probabilities when n is 5. So again, I'm just going to show you the states corresponding to a permutation that starts at 1 because of the circular symmetry. And I'm also, for simplicity, setting the y's to be 0, just to make things a little bit less busy on the right-hand side. And as before, I'm also renormalizing my steady state probabilities by putting everything over the same common denominator and then ignoring that common denominator. So what you see when you look at these probabilities, that at least experimentally, they seem very closely connected to Schubert polynomials. So most of them look like monomials times the product of Schubert polynomials. And let me explain my notation here. So what does x to the 5 to 1 mean? That means x1 to the 5, x2 squared, x3 to the 1. So all these x factors are just monomials in the x variables. And then most of the time, my steady state probabilities look like they're monomials times products of Schuberts. But there are a few exceptions. This one is a sum of Schuberts. This one is also monomial times sum of Schuberts, and same with these two. So there's 4 that look a little different. But even those that look different seem to have the pleasant property that they're positive sums of Schubert polynomials. Okay, yeah, so that's what I just said. The probabilities seem to have nice expressions in terms of Schubert polynomials and are often products. So I can say something about those that are products of Schubert polynomials. I just need to make another definition. So we say that a permutation W avoids the pattern 2, 4, 1, 3 if there are not 4 positions I, J, K, and L such that the letters of my permutation, Wi, Wj, Wk, Wl, are in the relative order 2, 4, 1, 3, meaning that this one is smallest, this is second smallest, this is third smallest, and this is largest. So as an example, this permutation 3, 4, 6, 1, 2, 5 contains the pattern 2, 4, 1, 3, which I've shown in red, because those red letters 3, 6, 1, 2, 5 have the same relative order as 2, 4, 1, 3. But the permutation 1, 2, 6, 4, 3, 5 avoids the pattern 2, 4, 1, 3 because you cannot find 4 positions where the corresponding letters are in the relative order 2, 4, 1, 3. Okay, and now we say that a permutation W is evil avoiding if it avoids all the patterns 2, 4, 1, 3, 4, 1, 3, 2, 4, 2, 1, 3, and 3, 2, 1, 4. And we call them evil avoiding because of this mnemonic. If you replace 1 by I, 2 by E, 3 by L, and 4 by V, then these 4 patterns become the anagrams evil, vile, veil, and leave. And yeah, so that's the only way I can remember this definition is through this mnemonic. Okay, so then we have a theorem that whenever W in Sn is an evil avoiding permutation representing a state of the inhomogeneous ASEP without loss of generality, W sub 1 is 1, then the probability psi sub W, so the probability of being in that state, is proportional to a product of K double Schubert polynomials, where K is the number of descents of W inverse. And we have a totally explicit formula, but I don't really want to go into the details of that. So, so recall in our example, when n is 5, there were 4 bad states whose steady state probabilities were not products of Schubert polynomials, and they correspond exactly to, I think this one corresponds to evil, and then this one is vile, this one has the bad pattern veil, and this one has the bad pattern leaf. So the 3, 5, 2, 4. The 3, 5, 2, 4 has the same relative order as evil, where this was supposed to be 1, 2, 3, and 4. Okay, so these 4 words correspond to the four bad states when n is 5. So so it's still a conjecture that all of our probabilities are positive sums of Schubert polynomials. I should say a monomial times positive sum of Schubert polynomials. But this conjecture and this positivity here makes one wonder, is there a geometric interpretation for all of these probabilities? So since Schubert polynomials represent cohomology classes of Schubert varieties and the complete flag variety, is it possible to define some kind of subvarieties, some family of subvarieties in the complete flag variety whose cohomology classes correspond to these steady state probabilities? So that's a question, or yeah, wide open question. So let me just summarize what we've seen. We've seen these 2 different models of particles hopping on a circle, the multi-species ASEP and also the inhomogeneous ASEP. These are the pictures to help you remember their definitions. And in both of these models, multi-line cues can be used to understand the probabilities in both. In the first case, this was due to Martin, and then we gave a new proof with Cortila and Mandelstam. And in the second case, Iyer, Linnison, and Arita Malik have understood probabilities in the inhomogeneous ASEP only in the case yi is 0. Otherwise, it's actually not known. And these 2 models, respectively, are connected to Macdonald polynomials and Schubert polynomials. And so I guess that the takeaway is just that connecting these probabilistic models to combinatorics can lead us to new conjectures, results, and applications on both sides. So, so thank you very much. Here's pictures of my co-authors.